Hi, I am Athman. In this presentation, I will speak about Darbandikhan Dam and Darbandikhan Lake, which is one of the most beautiful places in Iraq. The Darbandikhan Dam is a multi-purpose embankment dam located on the Diyala River, approximately 65 kilometers southeast of Suleimaniye city and 230 kilometers northeast of Baghdad city in Iraq. It was constructed between 1956 and 1961. Due to poor construction and neglect, the dam and its 249 megawatt power station have undergone several repairs over the years. A rehabilitation of the power station began in 2007 and was completed in 2013. The purpose of this dam is irrigation, flood control, hydroelectric power production, and recreation. After Tahar, the engineer company of USA designed the dam. Construction began in 1956. The reservoir began to fill in November 1961. The dam was complete that same year. After the reservoir filled, several problems occurred. In 1967, there was a major slope failure about 100 meters upstream of the dam. This and other slope failures are continually under repair. The bedrock beneath the dam has to be regrouted, and the cracks of the dam settled too much, required it to be repaired. The riprap on the upstream face of the dam was also repaired in 1999 and 2000. And as you see in figure, riprap, rock armor, or rubble, it is human-placed rock or other material used to protect shoreline structures against scour and water, wave, or ice erosion. Between 1983 and 1985, the dam's power station was replaced by German and Japanese companies. The original 2 by 800 kilowatt generators were replaced with the current power plant's 83 megawatt generators. The generators were commissioned in 1990, after the political situation in the country calmed. However, two of the generators were not commissioned correctly, and the turbines suffered from severe cavitation. As you see in figure, cavitation is a phenomenon in which the static pressure of the liquid reduces to below the liquid's vapor pressure, leading it to the formation of small vapor-filled cavities in the liquid. When subjected to higher pressure, these cavities, called bubbles or voids, collapse and can generate shock waves that may damage machinery. These shock waves are strong when they are very close to the imploded bubble, but rapidly weaken as they propagate away from the implosion. New spillway gates were installed between 1989 and 1990, after they were removed in 1988 because of the Iran-Iraq war. During the war, the spillway and substation were damaged from bombing. The power station was damaged from bombing in 1990 as well. In 2007, the World Bank began a 35.36 million US dollars project to repair the Darbandikhan and Dokkan dams. Repairs to the Darbandikhan dam cost $18.85 million and were completed in 2013, resulting in 1% for availability. The dam is located within a gorge on a foundation of sedimentary rocks. It is a rock-fill embankment type with a central clay core. The dam is 128 meters high and 445 meters crest long. Actually, it is 535 meters long if the spillway section is included. Its crest is 17 meters wide and at an elevation of 495 meters, the structural volume of the dam, including rock, clay, and filters, is 7,100,000 cubic meters. The dam collects water from a catchment area that covers 17,850 square kilometers. Its reservoir, by design, has a storage capacity of 3 cubic kilometers. At normal pool level, at an elevation of 485 meters, 2.5 cubic kilometers of that capacity is active or useful storage, while 0. 0.5 cubic kilometers is dead storage. However, due to 57 years of sedimentation, the current total storage volume is less than the design one. Now it's about 2.5 cubic kilometers. At normal elevation of 485, the reservoir covers an area of 113 square kilometers. To protect the dam from flooding, it is equipped with a controlled chute spillway on the right abutment adjacent to the dam embankment. It is controlled by three 15 by 15 tainter gates. And as you see in figure, the tainter gates is a type of radial arm floodgate used in dams and canal locks to control water flow. At the terminus of each chute, there is a sky jump to help dissipate energy. The maximum discharge capacity of the spillway is 11,400 cubic meters per second. The dam's power plant is located at its toe and contains 3 of 83 megawatt Francis turbine generators. They are each afforded a rated hydraulic height of 80 meters and can each discharge 113 cubic meters per second. Above the tail race for each turbine is an irrigation outlet. Each of the 3 outlets can discharge up to 175 cubic meters per second downstream. As you see in figure, the Francis turbine is a type of water turbine. It is an inward flow reaction turbine that combines radial and axial flow concepts. Francis turbines are the most common water turbine in use today and can achieve over 95% efficiency. During earthquakes, the earth crust vibrates in all directions, both horizontally and vertically. For embankment dams, the earthquakes may cause lateral and longitudinal deformation in the dam, which in turn may cause settlements and form longitudinal and transverse cracks. The damage and deformations occurred due to the earthquakes may lead to near failure or even full failure. The settlement may cause freeboard reduction, which in turn may lead to overtopping risk. The longitudinal cracks may lead to dam slope instability. The transverse cracks may cause initiation of internal erosion and the dam failure due to piping, depending on whether there are adequate filter zones to stop the erosion. Accordingly, one of the most serious problems for dam engineers and the public is dam safety under strong earthquakes. A strong earthquake with a moment magnitude of 7.3 occurred on 12th of November 2017 near the Iran-Iraq border, 220 kilometers northeast of Baghdad, Iraq. According to USGS 2021, it was the most disastrous earthquake that has affected the Iran-Iraq border since 1909. The earthquake had lasted for about 30 seconds, which is long duration. At the time of the earthquake, the water level in the reservoir was at elevation 471.92 meters, about 13 meters below the normal operation level, and about 23 meters below the crest. Furthermore, the reservoir level had been low for about 6 months prior to the earthquake. Therefore, the upper embankment materials can be considered as non-saturated part at the time of the earthquake. However, the embankment experienced notable deformation at the crest. After the earthquake, many experts of engineers and geologists have immediately visited the dam to check its safety and provide instructions for dealing with the new situation of the dam. As an instant safety measure, the reservoir water level was gradually reduced during 1 week, about 1.9 meters. The data collected in two stages, visual inspection and detailed inspection. The aim of the survey was to determine the locations of cracks, displacements, and abnormal appearances that caused by the earthquake. The horizontal and vertical offsets of cracks were measured. The movements and settlements were determined relative to control points located on bedrock. The cracks occurred due to earthquake were mostly along the crest of the dam that run mainly in the longitudinal direction, which is the most common type in dams subject to earthquake, and some transverse cracks at the abutments, and these are the most dangerous ones, which pose a greater threat to the safety of the dam. The maximum width of the longitudinal cracks is 14 centimeters. The width of the major transverse crack that occurred in the clay core next to the spillways structure was about 16 centimeters. So, the estimated depth of the major crack should be between 2.4 and 11.6 meters from the top of the clay core, meaning that it may go under it may go down from elevation 490.6 to 479 meters. However, there were no differences in elevation between the two sides of the transverse cracks on the crest of the dam, except that one next to the spillway wall. The maximum crest settlement was about 48 centimeters and increased immediately after the earthquake to 61 centimeters after 13 months. The increased values in the settlement can be attributed to either dissipation of the increased pore water pressure due to the earthquake or due to the post shocks. Many fallen rocks from the high steep mountains surrounding the dam were observed on the crest of the dam, especially near the abutments. The size of the rocks ranged from a few centimeters to more than 2.5 meters in diameter. The cracks and fallen rocks were then documented. Several test pits were dug at the cracks locations. All the cracks on the crest were superficial cracks. They only penetrated upper 2 meters of the road subbase on the top of the dam. The cracks haven't penetrated the core except the transverse crack next to the spillway. In order to check the condition of the clay core at the area close to the spillway, 3 boreholes at 3 locations close to the spillway were drilled using a continuous method of drilling. Visual inspection was then carried out on the extracted cores. In addition, to check the strength of the clay core, an in situ test was carried out on the clay core samples using a pocket penetrometer instrument. Once the safety of the spillway and the bottom outlets has been checked, the water level in the reservoir was then gradually lowered 2.9 meters from the elevation 471.9 meters to the elevation 464 meters in about 2 months. in order to investigate the lower parts of the dam and to reduce the water pressure applied to the dam. Due to the awareness and cautions about whether there were cracks in the lower parts of the dam or not, the water level wasn't allowed to rise above elevation 470 meters during 2018. However, in 2019, based on the results obtained from the drilled boreholes and on the promised information regarding the behavior of core rockfall dams (ECRD) subject to major earthquakes, it was decided to gradually raise the water level in the reservoir. The decision of rising water level in the reservoir in 2019 was based on the academic findings and observations mentioned in Pills and Fills 2002. However, the upstream and the downstream wide cohesionless filters will contribute to the crack filling or self-healing process if any crack exists in the core. From all of these analyses and the results of the various investigations, the authorities of Darbandikhan Dam concluded that there were no problems severe enough to threaten the safety of the dam, and that the dam was safe and could store water to its full capacity. Accordingly, in May 2019, the water level in the Darbandikhan reservoir was raised to the elevation 484.28 meters, which is only 0.72 meters below the maximum operational level. Based on the deformations caused by the earthquake, the dam suffered minor to moderate damage. In addition, based on the UNSW method for assessing the probability of piping failure, since it was designed and constructed adequately, the Darbandikhan Dam has low chance to fail by piping under static condition. Furthermore, at the time of the earthquake, the water level in the reservoir was low. Therefore, the dam performed satisfactorily and survived from the earthquake. Thank you for listening. If you have any question, you can find me at my email.